It's about the CMB mostly. And we will start with Miguel Cuartan from the Universidad Federal de Rio de Janeiro about the first constraints on the intrinsic CMB dipole.
So yes. So I cannot say I'd like to thank the organizers for the invitation, but anyway, so let me share my screen here. Hopefully it's gonna work flawlessly. Just to go through quickly what, so you have my screen, I guess. But okay.
Yes.
So this is a work I've been pursuing on and off for the last 10 years, right? Since we started with the idea of measuring on Planck or on the CMB, this effect of aberration and Doppler, which means that you have this change in positions of the hot and cold spots, and also a modulation due to Doppler. So back 10 years ago, almost 9 years ago, we made this prediction for the signal to noise in different experiments, and we found that Planck could get a good measurement of this, and then Planck carry out this measurement a couple of years later. But there's some caveats to these measurements. That's what we want to point out, is that part of what Planck measured originally in 2013 is not new information. It's just a dipole in a different disguise. So, and this is what we call the dipole distortions work I've done with Alessio. So in this work here, we try to focus on, let's try to get the most possible information that is complementary to the dipole, with not affected by it. So it's orthogonal, let's say, to the dipole. And that's how we measured aberration and measured Doppler, but by removing this contamination from the dipole. And we get some nice results. We get measurements of the velocity through aberration, Doppler, and boost. A boost is just a Doppler and aberration in the same direction in the sky, which means that they are not independent. But if you want to measure the intrinsic CMB dipole, then its effect on these components of aberration and Doppler, you want to allow that the aberration Doppler point in different ways, because if you have a primordial perturbation, say a lensing, which is dipolar lensing effect, we produce aberration only. If you have different kinds of temperature fluctuations in the primordial sky, you produce some Doppler effect. So we want to measure them separately. And we did it then in both temperature and polarization. The aberrations here, the Doppler is there, and they are consistent with each other. And this means that it looks like the traditional interpretation that the CMB dipole is just velocity is correct. But it's interesting because you can allow to put constraints on the primordial intrinsic dipole, and that's what I did with Pedro Ferreira, the other Pedro Ferreira, not the one you heard the other day. So there's some degeneracy of Pedro Ferreira's, and so we can exclude the null hypothesis with 6 sigma, which means that there's no couplings in the high multiples. And we can put some constraints on the intrinsic CMB dipole. I think is the first constraints I ever put, which is they cannot be above 3.5 millikelvin at 95% confidence level. And this is set to improve with different future experiments which go to higher multiples on the CMB. So that's interesting because we know that the quadrupole, octupole, there's some claimed anomalies. Maybe the intrinsic dipole, if you measure it, you bring some new information. That's the 2-minute summary.
Thank you, Miguel. So
let me unshare.
Yes, please.
Okay. So shall I share my screen?
You're mute, Nelson.
Yeah, sorry. So Claudia.
Hello, can you hear me?
Yes, we can.
Yes?
Well, it's very, very low.
Yeah, it's a bit faint.
So I share my screen. Can you see this?
No. You're not sharing at the moment.
She just froze. No, she's
no. Now, yes. Now we see your screen.
Yes?
Yes.
Okay. Well, I will use it. Okay. My talk, which is recorded, is about the current status of the QUBIC instrument. QUBIC is an international collaboration that aims to put an instrument in Salta, in Argentina, to measure the B-mode polarization in the CMB, the primordial B-mode, the primordial gravitational waves. Yes? Imprint, of course, in the polarization of the CMB. So QUBIC is a novel instrument which has a special infrastructure. It's an interferometer and a bolometer at the same time. So in this picture, you can see it's a cartoon of the infrastructure. So the light goes through a hallway plate and a polarizer. Then it goes through an array of horns that produce an interference pattern that has this shape that you can see here. Yes, it's a particular synthesized beam. It's with multiple peaks. Then, well, after collimating here, we can detect in two, separating the signal in two frequencies bands. We can detect them in two focal planes, one at 150 gigahertz and the second at 220 gigahertz. And these focal planes are covered with bolometers. So this is a very interesting instrument in the sense that you have a good control of systematics because it is an interferometer, so you can do auto calibration, for example. You can control, you have several ways of controlling the systematics effect. But also you have the detector are bolometers, so you have a very high sensitivity. But it turns out that thanks to the particular synthesized beams, which has these multiple peaks, which separation depends on the frequency, we have the possibility of doing spectroimaging. What does it mean? It means that in each of the focal planes, in each broadband, let's say, you can construct at the map making level, you can do maps at different subfrequencies. So instead of having 2 frequencies, we can have 10 frequencies, 5 at each broadband. So this is very important in an experiment like this to separate the foregrounds from the CMB signal. So to separate the foregrounds, in particular the emission from the dust in our galaxy, it is very important to have measurements at different frequencies. And Cubic is very good at this, no? So you can ask me a question about the details of the experiment if you want, but well, Cubic has a particular properties of the noise. It's correlated both in the subfrequency bands and also spatially, and all is due because of the particular synthesized beam with the multiple peaks. But we have found that, let's say, our predictions for the bounds that we can put on the R parameter, which measures the tensor to scalar ratio, is of the order of 0.015 at 1 sigma, yes? So this is quite smaller than previous, that current results on bounds on the R parameter, yes? So a series of papers has been released very recently. You can find them on the archive and soon on the journals. Well, if you have any question on this, also on the BMOS polarization, I'm happy to answer your question.
Thank you, Claudia. So next we have Mario Duspi from the Instituto Espacial de Orsay about SC clusters as cosmological probes.
Yeah, if I can just share the
Yes.
few slides. Okay. Can you see my screen? Yeah, it's reversed. Okay, so first of all, I'd like to thank the organizers and also apologize for not attending the first session every day because I'm teaching until 6 p.m. French time, so it's now. So I cannot attend the first part of the meetings. So the work I was presenting is about cosmological clusters as cosmological probe on the point of view of both the constraints but also the systematics. And it's a kind of a review, a compilation of few papers we did along the last year, starting during the Planck analysis, both on SD clusters and SD map. And then I also show some recent work we did on using clusters in future optical surveys. So just to summarize the main results, one thing we've shown is that the tension that we have seen in the first papers in Planck in 2013 between the best or the preferred cosmology from CMB and from SZ clusters, which was like 2.5 sigma at the beginning, has moved and is much reduced now. And this is mostly due to the fact that the optical depth of the reionization is now well constrained, and it moves a bit the CMB contours towards lower sigma 8 because tau is lower. So putting it more in agreement with SZ clusters. But still, what we really want and what we need for using the full power of clusters in general and SZ clusters is to have access to the mass of the clusters. And we do that through the hydrostatic estimates, hydrostatic mass estimate, M500 HE. But we know that it's not exactly the true mass of the clusters, and we put all the physics that happen in the clusters inside of small parameters 1 minus b, which changes the true mass M500 compared to the one we measure. And obviously, a lot of people are trying hard to find these bias estimates, and you can do that through simulations. And this is the purple part on the right of the graph, where you see that this evaluation of 1 minus b by simulation is always above 4.8. You can also do that by measuring weak lensing, because with weak lensing of and strong lensing of clusters, you can have access to the total mass. And as you can measure with X-ray and SZ, the hydrostatic mass as well, you can compare the two and have an access to 1 minus b. And you have many estimates. These are the black dots with error bars along the last years. And you see that there's a lot of dispersion, but the average of this value is around 4.8, let's say. And what you need, if you really want the CMB and SZ clusters to be right on top of each other, is a value of 0.64, which is needed by the CMB, or pushed by the CMB. So you see that there is a small divergence in the estimates of this hydrostatic mass bias. So what we did to infer it independently of the CMB and on the optical was to use two information that we had in Planck from the SZ part, which was the SZ number count, cluster number counts on one side that we were using for doing the blue contours on the left, but also the SZ map, from which you can compute the angular power spectrum, and which depends as well of cosmological parameters. And when you combine the two, you get the big ellipse in green in the top, where you can measure more or less at the same time sigma 8 and the mass bias without any prior on this mass bias. And we found a preferred value, which is around 75. Obviously with large error bars, because SZ clusters and SZ maps give probes that are quite degenerated, so we don't have a strong handle on all the parameters. But still, it's higher than what the CMB wants, and there's still a small tension between the two estimates of the bias. So something we looked as well was to understand if this assumption of having only one parameter, this 1 minus b for all clusters at all redshifts and all mass, is really a good assumption, because it may vary with time, it may vary with the mass of clusters. So we allow for freedom in evolution of this mass bias as a function of redshift and mass. And what we show is that it doesn't help at all in reducing the tension between CMB and clusters, because again, if you see the green banana on the bottom, it enlarges the contours, obviously, because you have more freedom, but it doesn't go in the direction of the CMB. And then what we noticed is that we tried to remove as much as possible any systematics in the SZ analysis. And we ended up including them and marginalizing over them. But every time we find kind of low value of sigma 8 compared to CMB. And this is not true only for SZ. This is true for other clusters in X-ray, for example. And this is true also for other large-scale structure probes at low redshifts. And this is a compilation of a few results coming from weak lensing tomography in kids in CFH-TLS and clusters. And they are all with big degeneracies, but always below the contours of the CMB. And then we were interested in what can we say, what will we be able to say using next optical surveys like Euclid, LSST, or WFIRST, because we will have like tremendous amount of clusters. And so the statistic won't be a problem anymore, but obviously you will still have systematics. And so on the top plot, what you see is the errors of, for example, on omega m for the 3 surveys in 3 colors. But depending on how much you know the scaling relation between your observable and the true mass of the clusters. And if you have 10% uncertainty on your scaling relation, basically you have some precision. The number doesn't really mean anything. But if you're able to go down to 1% error on this scaling relation, then you gain a factor of 4 on the uncertainty on omega m, which means also that if you're not able to go to 1%, you lose a factor a few on the precision you may have using clusters. And it's even worse if you make a wrong assumption on the mass function you need for estimating the cluster number counts. And we did some simulation by simulating a survey with a Tinker mass function and using a Des-Palimax function to analyze it. And what we find is like 8 sigma difference between the 2 values found for the parameter of the equation of states. So again, you need to know really well your theoretical assumptions, and one of them is the mass function, to get accuracy on your cosmological parameters. Thank you.
Thank you, Mario. So we can go to the last summary from Hideki Tanimura from Université Paris-Saclay about detection of kinematic Signal-Sadovich effect in clusters of galaxies. You can share your screen if you want to show some slides.
No, I don't have a slide. I think my video was the shortest one in all the talks. So I think I hope it was clear. Just to summarize in words, not slide. So hi, I'm Hideki Tanimura, postdoc at IAS in France. First, thank you for the organizers to open this nice conference in this busy but period, kind of. And thank you for giving me a chance to show my work. And my talk is about the detection of the kinematic Signal-Sadovich effect, KC, in galaxy clusters. This is a work with Nabila Ghanim and Salim Zaoubi. As you know, the KC can be used to constrain the cosmology, such as growth rate of structure along the cosmic time. But our result was so far not sensitive to cosmological parameters. So in our study, we used the KC to trace the distribution of gas in galaxy clusters. This information is important because the gas distribution in clusters, for example, gas mass fraction in clusters, gas mass over total mass, is sometimes used to calibrate or check baryonic effects in hydro simulations, especially for AGN feedback. For now, gas fraction in cluster is mainly measured in X-ray and ST, but it's not well constrained. For example, if in some result, the gas fraction is consistent with the cosmic baryon fraction, but if you look at other results, the gas fraction is not consistent with gas mass, not consistent with cosmic fraction. And there is a deficit of baryons in clusters compared to the cosmic fraction, most likely due to the baryonic effect in clusters, which pushes the gas inside to outwards. So it is important to investigate the gas distribution in clusters to constrain the baryonic effect. That's about my work. Thank you.
Thank you very much, Hideki. So now we can have a short presentation, short summary from the posters. Is Shaner here? Shaner Omar? I don't see him in the participants. So maybe we can go straight to Raúl Enriquez.
Hello, everybody. My name is Raúl Enriquez. I am studying the PhD at Universidad Autónoma de Chiapas in Mexico. My poster is about CMB spectral mood distortion associated to an alternative dark matter model with a phase transition at early universe. In this work, we put some constraints with FIRAS and PIXI sensitivity for our three parameters in this dark matter model. Thank you.
Thank you, Raul. So we can now open the floor to questions to speakers or about poster. Please raise your hand if you want to make a question. Let me give an opportunity to participants to start with questions. If not, I can start. While you think about questions. So I wanted to ask to Marion. So when you mentioned that the simulations have been used to place constraints on the mass bias, I was wondering, because you show only one band for the measure for the estimate. So has this been measured in simulations with different feedback mechanisms? I don't know, just to make sure that it's not only due to the single subgrid physics that are used in one particular simulation.
Yeah, what we did back in 2013 was to use 12 different simulations and using the relation between the true mass and their estimated hydrostatic mass from halos to have some kind of average value of this bias with 12 simulations. And we ended up finding a value of 0.8, but every simulation find a value above 0.7. And in recent simulations, people did that again, putting more feedback, more AGN feedbacks, more baryonic physics, etc. And so I didn't do again the compilation myself, but every paper I've been reading finds value above 0.8. So it's kind of an average of all the publications doing this kind of stuff, which falls always between 0.8 and 1. That's why it's a big band and it's not really an error bars or whatever.
Okay, so so it's not easy then to do that.
Yeah, you really have to work really hard to make any baryonic processes make the equivalent of a 1 minus b of 0.6, basically, which is needed by CMB. It's not seen even in the kind of extreme baryonic things that we have now in simulations.
Yes. So could there be some type, I mean, these simulations, are they also treated as CMB photons and make them go through the same processing as the observations? I don't know, maybe there's some bias there, or is that ruled out?
I mean, it's not ray tracing stuff. It's just knowing the mass by the whatever algorithm you have, friend of friends, and blah blah blah. You most oftenly is done by repeating X-ray-like emission more than SZ, and that's from the X-ray they got the hydrostatic mass.
Thanks very much. So co-hosts cannot raise hands. So I saw that Hideki wanted to ask a question before Martin. So let's go to Hideki first.
Yeah. Yes. Can I ask to Claudia about the cubic experiment? In the talk, you didn't mention about the noise from atmosphere, but it's a really big challenge for to detect B mode, especially primordial B mode from the ground. What's the status of what are you going to do? What's the view of to remove the atmosphere noise?
So Well, first of all, we will be observing during 9 of the 12 months because of this special.
Claudia, sorry, can you speak closer to your microphone?
Sorry. Can you hear me well? Now, can you hear me?
It's a lot better.
Okay, sorry for that. So I was telling you, we won't observe in the winter, yes, because of the weather, because of the bad, let's say, atmosphere conditions. But then the rest of the 9 months, the condition of the site are quite good, yes, comparable, almost comparable to the original site in the South Pole that were the original site for cubic, yes. But we have models for the atmosphere because I mean the site, since it's the same as Shama radio telescope that will be put in the same site. We have been studying the conditions, the atmospheric conditions for a very long time, and we will put an atmospheric model to consider the noise in our analysis.
Okay. So you can remove by model. So is there some estimate of
measurements? Yes.
Okay, measurement. Yeah.
Yeah.
Is this an estimate of kind of how much % contributes to the how much % of noise contribute to the signal or something from the atmosphere?
We actually were working on that at this moment. We are implementing the atmospheric model in our simulations, so I cannot give you a number now.
Okay.
But we are working on that. On
okay.
The simulation group.
Okay, thank you.
Okay, so Martin de los Rios has a question.
So I think Rogerio was first. So Rogerio, no, you are my boss. You.
Go ahead, Martin. Go ahead.
Okay. So my question is for Miguel. So maybe it's a very naive question, but well, I am very interested on your work. So and you explained a bit on the video, but I would like if you can expand a bit more. So as I understand, the current constraints are completely. I mean, are completely with no dipole, with no intrinsic dipole. But my question is regarding what happened if we indeed have an intrinsic dipole. What happened? I mean, I assume that if we have an intrinsic dipole, the velocity dipole will be lower. And I was wondering if this can, for example, shift the cosmological parameters that we infer, or if this can create some anomalies as the anomalies that the people found on the CMB or these kind of things.
So Martin, your question is very open, very broad, right? So it is consistent with no intrinsic dipole. I don't think that's very surprising because, as you see, the current error bars allow still a 10⁻³ intrinsic dipole, which is almost the whole dipole could be the intrinsic dipole still at 95% confidence level. So, but if you did find one, doesn't matter now or in the future, it has consequences. First of all, it means that the velocity that people assume that is the solar system velocity is wrong. So this 369, 370 will be wrong. And this is very important because this velocity is used all over astrophysics to convert measured redshifts into heliocentric redshifts. For instance, in supernovae surveys, they use this, they correct the redshift. So this has implications, okay? Now, in the parameters of the CMB, I don't think the implications are so large. I don't think so. But it would, then if you measure some intrinsic dipole, that means that, of course, you may not have single field inflation. You may have some isocurvature fluctuation. So it may or may not help to explain the claim anomalies in the low multiple CMB. It depends a lot. It's very model dependent, your question, right? So if it just means that either you don't have single free inflation if you detect different Doppler, as I said, couplings, or that you have a sum of the two components. And you said, if I do have intrinsic dipole, then the velocity is smaller. It could be even larger, right? It's a sum of vectors. So if the intrinsic dipole is pointing opposite to the velocity could be even higher. It could be that you have 500 kilometers per second velocity and an opposite intrinsic dipole. In fact, it's puzzling because on the radio galaxy, in the radio sources, you find a dipole which is very large, which naively will mean over 1,000 kilometers per second. And as far, I'm not an expert, but as far as I understand, no one knows what's going on exactly there. So, naively you could think, okay, maybe the velocity is 1,000 kilometers per second, 800 or something, and I have intrinsic dipole that partially cancels it. But that is now excluded, right? So whatever you have in the galaxy must be some systematics or something else we don't understand. But I don't know how to answer better your question because it's very open, right? It means that we are changing something fundamental in the model. We don't expect to have a 10 to the minus 3 intrinsic dipole in the standard paradigm of single field low inflation and lambda CDM.
Perfect. Thank you. Thank you.
Okay, so Rogerio.
Okay, so my question is for Maria. So I saw that you have a plot where you combine cluster counts and CLs. And I just wonder about the covariance matrix that you used. The reason I'm asking this is probably, I'm sure you know Fabian Lacasa, right? So Fabian was a postdoc with me here in São Paulo, and we worked exactly on the joint covariance matrix of number counts and CLs, taking into account supersample covariance. So I just wonder what you're using.
From now, for the first study we did in this paper, we assume no covariance at all between the two probes, which is bad. But also because the cluster that we were selecting in the number counts are really local clusters and the massive ones, and they basically contribute to 1/3 of the power in the map, the Y map. So it's still a lot. I mean, it's not completely independent. The two samples are completely not independent, and we should use the covariance. But it's a bit less that we can think of because of the choice of the clusters.
So Fabien has a code now that he can compute this covariance. So he can just get this code. Thank you, Maria.
Oh, Miguel, go ahead.
I have questions, so for many people, but one at a time. So Claudia, I have a question for you on the cubic, right? So I'm trying to understand how cubic compares to the bicep array a bit, and in particular, so as understood, the cubic has two frequencies, two main frequencies, right? 150 and I don't remember now, 220 or 95. 220, and then 220 and 150. So I mean, I would, after all the bicep, let's say, press release fiasco, I'm very worried that if you have too few frequencies, you might have foregrounds in your analysis. But then you said that the frequencies, you can measure some small, variations inside each band. Does that help to clean foregrounds? The fact that you can measure the differentiate between 140 and 160, how much better can you clean foregrounds because of that? It was not clear to me.
No, so I didn't show these results in my talk because I am working on this right now on the separation of component separation, actually, yes. But we did in one of the papers, in the second paper is cubic 2, that studied the spectroimaging aspect of cubic. So in that paper, you can find the results of the, even with the technological demonstrator, which is a smaller version of cubic that has only one focal plane at 150. Yes, even doing the spectral imaging there, you can characterize the foregrounds. So we have made simulations in which you can in the map, yes, measure the spectral index of if you simulate that the map is dusk, yes, you can recover the spectral index of the dust. So as I said, so I don't know if it is clear, but the idea is that since you are mapping the sky with a synthesized beam that has this particular shape, no? That the secondary lobes depends on frequency. You can separate, but at the map level, no? You can separate in different maps, which will be correlated. The noise will be correlated, of course, anti-correlated between adjacent subbands. And also you will have a spatial correlation in the map because you will be correlating points separated exactly the angular separation of the peaks, yes? But even when you have this complicated noise behavior, if you put the correct covariance matrix of the maps, you still have information of different frequencies. You still have valuable information at different frequencies, and this is very important to separate the foreground. Yes.
Is this unique to QBIC from all these next generation ground experiments?
Yeah, yes, it is, because this you can see that we are obtaining with in the same focal plane. Now, in the full instrument, QBIC will have 2 focal planes. Now with bolometers, covered by bolometers, yes, and in that sense will be like as any other instrument that has bolometers, that detectors are bolometers. Even in this situation, QBIC has a special characteristic, let's say, which is the control of the systematics, because the systematics is a very strong problem in this kind of measurement where the signal is so weak. It is very important, and the foregrounds are so high, no? But even, I mean, the signal is very, very weak. So you have many kinds of systematics error you can have in your instrument. But since QBIC is an interferometer, because you have an array in the full instrument, you will have 400 horns in your array. So you have multiple baselines that are identical, yes, so it's how to say, redundant baselines, and you can observe the same sky with a combination of baselines. Now that you should have the same map, and if you don't have the same map as a result, you are seeing the errors you are seeing the semantic effect. You understand? So QBIC as an interferometer has a very good control of the systematic. As a bolometer has a very high sensitivity. And this is particular of this kind of instrument, which combines the 2 characteristics, yes? And like a gift, no? The fact that the synthesized beam has this particular property that the secondary peaks depends, the separation depends on frequency, that was something that came afterwards, let's say, because, and we could take advantage of this and propose the spectroimaging procedure. So this is something more, no? So we have 2 frequencies, which is good for foreground detection, yes, or foreground separation. But moreover, we have the possibility of having many more subbands. So we expect that this will be very useful for component separation.
Very, very interesting. Thank you.
No, okay.
So we can move on to Camila Novaes.
Hi, I have a question to Miguel. It's about the Mawide projection you showed in your slide, and it is curious that for the Doppler effect, your results point to the galactic region. So I was guessing how you deal with the residual contamination or the masking of your data. And I have another question, but I will enter in the line.
Okay, hi Camila.
Hi.
Nice to see you. So yes, let me share the screen. Maybe then I talk becomes a little better. So, but anyway, the point is, it has some curiosity. There's something which is curious, that it does point to the galactic plane. And I don't know if you noticed, I didn't want to draw too much attention to this, but it also points to where people called as this hemispherical anomaly, this dipole anomaly. It's very close to the hemispherical anomaly direction, which is, we find it interesting. Although I don't know if it's, we didn't want to draw too much attention to this because they're different scales. Okay, so we're not claiming that it is related. So I don't know, do you see the plots here? Are you seeing my screen?
Yes.
So anyway, so yeah, this was, I think, is what you're talking about, right? This clustering here, right? At higher Lmax. So so this is very close to the hemispherical anomaly, but there are different scales because this is dominated by high multiple small scales, and the hemispherical anomaly is below L of 100 or so. Anyway, now how do we deal with the mask? Is I had to skip all the details. You can find it on this paper here, but I will summarize here, which is we did brute force simulations, okay? Which means that we made heel peak simulations where we put the mask, and then we run the estimator in this mask simulation, okay? And then you calibrate on the mask simulation, which has the mask and the isotropic noise of Planck, which is relevant in this case. And on these simulations, you calibrate your estimator. So we have the estimator without a mask, without noise, and we take that as a first step. And with that, we calibrate with the mask and this anisotropic noise. And we had to do that by brute force. So we simulated aberration in this direction, aberration in that direction, aberration in that direction. So we did it using 48 directions. So, and different points of the sky, assuming it can be here, 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 here. And at each point, we have a mask effect, which is complicated, but we correct for the average. So since I don't know the position, I have to correct for the average. So there's some residual, but the point is the residual is much smaller than the error bars. So since we have largish error bars, we can afford to have some 10, 20 kilometers per second residual because they don't matter in the end. But we did, in the full simulations, there's no bias towards the masking direction. But if you don't do this, you're right. The estimator gets completely wrong, especially on the perpendicular direction to the mask. Then it's completely unreliable if you don't do this.
Yes, yes. Thanks.
Camila, you said you had another question? You can go ahead.
Yeah, can I ask? Yes,
Yeah.
It's we can use the same plot.
No, okay, it's for me, okay.
Yeah, sorry.
Yeah, right.
In the same plot, you also mentioned that the Doppler effect is worse than the aberration to this goal. So is this characteristics dependent of the estimator you are using, or this is general?
No, okay. Good question. It's not. I don't know if I have a plot here. I think I hopefully do. Yeah, here you go. So no, this is depends. Okay. So aberration and Doppler, it depends on a couple of things, right? So aberration depends. It's depending on the spectral shape. So if you have wiggles on your spectra, like peaks and troughs, the estimator measure better because the estimator is proportional to the derivative of the spectrum. The Doppler estimator is insensitive to your spectrum. It can have any shape you want. It doesn't matter. It gets the same result. Okay. So, but so for the Planck, where you have the temperature, you have the wiggles, and for E-mode position, we do have the wiggles. So it's a little better the aberration than the Doppler. And here, what I show for TT and EE is the expected uncertainty. This is so in dash here is ideal uncertainty if you have no noise and no mask. And the Doppler is in yellow and the aberration is in blue. So as you see in TT, you always get smaller error bars, so the error bar in velocity in blue than in yellow. So there's more information. There's just more information on the Doppler, on aberration. It's just how it is. That's a property of TT. And EE even more, because EE is even more wiggly. Now, if you have a smooth spectra, for instance, we consider that some other paper measuring that on the TSZ maps, right? They are much smoother. They don't have wiggles. So there, the aberration signal is smaller, okay? So if your spectra is smooth, has low derivatives, you get more in the Doppler. If it has more derivatives, more wiggles, you get more aberration. That's how it is. It's, our results were close to the expected ones. So in a sense, we did as good as we can do with Planck, I guess.
Mm-hmm. Yes, I see. Thank you. Very nice work.
Thanks.
Okay, so do we have more questions? Mustapha. Mustapha wants to ask a question. Go ahead.
Okay. Yes, thanks. My question is for Marianne. And so I have actually a couple of questions. So the first one is, excuse me. The first one is when we look, for example, at the status in 2018. So you have between 2013 and 2019. So you have a reduction in the tension between the constraints. If I see the plot, it looks like it's mainly due to the ellipses or the confidence contour for SZ have moved. And so did you consider to use the like figure of merit to see what happened to your uncertainties, and also like why did the contours moved in an area where you got more consistency with Planck? Yeah.
I can share the slide again, if you don't mind.
I think it's slide 6. Excuse me.
Yeah, so there's really two effects. One is on the side of the CMB, which for the best value moves to 84 to 81 in terms of sigma 8. So from the middle of the black one to the middle of the red one. And on the cluster side, we also, the only thing that we changed and which has an effect is the prior on this mass bias. And we moved from the blue top hat prior that we had in 2013. And this is back to what I was saying about the simulation. We found a value of 0.8, but all the results were between 0.7 and 1. So we took a top hat. We didn't want it at this time to take a Gaussian because we have only 12 and in 2015, we moved to assuming a prior coming from weak lensing studies, and this is a red one. And you see that the main difference is that where we didn't allow anything between 0.6 and 0.7 in 1 minus B in 2013, now we allow between these two, and this makes allow the contours to be higher in sigma 8, because if you have a lower 1 minus B, you allow for a higher sigma 8. So there is really this combination of the CMB going down and allowing with this new prior some values a bit higher for the clusters, and we mix the two join together.
Okay, thanks. If I look to the figure, the previous figure 5 for 6, the following figure 6, I checked with just with my eyes, so it doesn't look like the CMB contours goes down. It really looks like the it looks really like the just the SC goes up. I was just curious also, did you consider, like, for example, the figure of merit to see whether you got better constraints with better data or what? Yeah.
Not we didn't compute any figure of merit, no.
Yeah.
We could have just to see how we move from one year to the other exactly. Yeah. We didn't do it. No.
Okay. If and following up on this, did you try, because sometimes this 1D or 2-dimensional contours, they actually, did you try to measure the inconsistency in higher volume of parameters? If you have any other parameters, did you try to use measures where you can kind of see the consistency for the overall parameter space?
So we didn't really measure the consistency, but we did this analysis with like 6 free parameters. I mean, the cosmological parameters, free, H0, NS, and whatever, except that for NS, we don't have a strong handle from the clusters alone. So we had to put the Planck prior. So obviously, by definition, they are consistent with between Planck and clusters. And And for the other parameters, we have for H naught, whatever remains, we have the good consistency just on the value and the error bars, but we didn't measure it in terms of distance, for example.
Okay, thanks.
All right, thank you very much. So maybe, oh, right, there's a question from Miguel.
I can ask if no one else wants. So I have a question to Hideki. So
Yes.
I was trying to understand, because I never got into I never understood the small details of the KSZ measurement. So your talk was interesting in this way. So in a way, you were discussing how to stack the signal from clusters in order to enhance, right, detectability. And then you said, well, if I just stack them all, they will cancel because some are positive, some are negative. But you know, if you select those that has the same radial velocity, I mean, going up, approaching or not, then you increase the sensitivity. Now, I understand that you have some largish error bar on the radial velocity still. So it means that when you're stacking, some of them will be still canceling because you thought they were pointing away from you, but they are not.
Yes.
So do you know more or less how much signal you are losing because of this wrong stacking, and how much this could be improved if you could do a perfect stacking?
Yes, thank you for the question. Yes, that's the main issue to detect the very weak KC signal. I know the how much suppressed by the noise from the velocity estimate. For example, you can use, I check with using the simulations. So using simulation, how much your estimate of velocity is wrong, you can check. And also it's relatively easily, the velocity estimate, so velocity distribution of galaxy clusters is basically a Gaussian shape. And you can get the true distribution, for example, just typically just a deviation of Gaussian, typically center of 0 and some deviation. And in some cosmology, the deviation is predictable. But if you look at your estimate, it's faster because of the error. So kind of easily you can estimate how much your velocity estimate is wrong. With this information, easily you can get how much KC is suppressed using simulation and the fatness of the velocity distribution. Yeah.
But do you have a short summary? I mean, instead of 3 sigma, how many would you get if you had perfect? More or less, just
yeah, more or less. More or less, it will be close to 5 sigma. Yes, I didn't clearly check, but I think it goes up to more than 4 sigma clearly. But I'm not sure if it will go over 5 sigma. So I say roughly 5 sigma. Yeah.
Thank you.
Yeah.
Thank you. So Antonio Monter has a question. Please go ahead.
Yes. Yeah, so it's also for Hideki, actually. Very nice talk. So I was wondering, so you're using stacking of the signal, of course, because the signal is too weak. Yeah. What's the expectation for actually, in terms of having individual measurements of the KSC effect with, future instrumentation, which is something interesting.
Okay, so it's a good question. Currently, I only know 1 or 2 examples. If there is a very high radial velocity, typically radial velocity of cluster is 300 kilometers per second. But in that case, it is more than 3,000 kilometers per second. So you have to have a very strong, currently you have to have a very high velocity. Also, it has to be a very massive clusters. It's pretty rare. And I don't have the answer for the future expectation. So
Yeah, I know.
it's difficult to say.
Yeah, even in my case, it's harder because I actually want to measure the spin. So I have to subtract the peculiar velocity, right, in order to see the rotation. So it's even harder, I think, because you're interested in the velocity, basically. In your case. So, but I was wondering if there's because I've looked at it, but it's unclear to me if the new instrumentation is actually gonna allow for samples of hundreds or thousands of clusters or not. It's anyways, I was wondering if you had.
Yeah, I'm not sure. Even maybe in the visual one, it's pretty hard. Even in a octuple, they're stacking.
Yes.
Of course, so that's why now in decades, I mean, it's pretty difficult to detect individual KC. But I think in my case, I couldn't estimate cosmological parameter, but after I attend this conference, maybe I can use a forward modeling to estimate the cosmological parameter with a stacked KC signal, even if it has a large error bar. Yeah.
Okay. Thank you.
Thank you. Now Jorge has a question.
Yes, it's for Miguel. A very naive question. So Gaia recently measured our acceleration. I guess this would also induce a dipole in the CMB since it's measurable, but it's probably very small. So have you thought about this? Did you estimate how big it could be?
Yes, Jorge. So as an acceleration does not produce a dipole. It's a velocity that produces a dipole. Now, in a way, you're right, because if the sun is moving around the galaxy, it has this centripetal velocity, and that does produce an aberration pattern. And in fact, I did think about this many years ago. I didn't pursue this, but it's something we are now thinking and discussing with my students if something new can be done in this way. But because then you have the velocity induced by the acceleration, right? So in order to measure acceleration, you need to measure velocity at two different points of time, which I did think of this with Alessio at some point. We measure velocity, then measuring 10 years ago, and the difference you can get measured acceleration.
But it's also, acceleration could be also, it's equivalent to a gradient of the gravitational field. So there could be also some other effect where you don't need, but it's probably very small. I don't know.
Right, but I think but I understand. I think it's small, because I think what Gaia is measuring at the end of the day is just the centripetal velocity of the sun around the galaxy. Now, acceleration, sorry. But I have to think about it. In the end, you're asking if a local gradient of local potential can affect, and I think not, but I have to think about this in more detail. We can discuss.
Okay, thanks. So I wanted to ask one last question to Raul. Maybe you can tell us a little bit about this bound dark matter model, how it compares in 2 sentences with cold dark matter.
Can you repeat the question?
I was wondering if you can compare the bound dark matter model to the standard cold dark matter for us.
The main idea is that this BDM model is like warm dark matter. The comparative is better with a warm dark matter. In this scenario is more exotic because we put a hypothesis that some little fraction or in this phase transition could be the spectral distortion, and this is for is a exotic scenario, but it's better to compare for warm dark matter. Okay. It's very similar in cosmology for Gorn Darmata.
Okay, thanks very much, Raul. So if there are no more questions, I think we can wrap up. So Rogerio announced that we will have the conference photo on Friday on the afternoon, so that we should all be there. And we'll meet again tomorrow morning, 11 a.m. Sao Paulo time. All right. Thank you to all the speakers, to the poster presenters, and everyone who's here. See you tomorrow.
Bye-bye.
Bye-bye. See you tomorrow.
Thank you.